So let me do another example. Just a discussion of an example system. And the system is a particle moving in one dimension. So how to describe it? We already had as part of our postulates, because particles are the most important systems in quantum mechanics. If you think about it, the way we conceive of the universe is just made of things which move around in space. And those things, we can subdivide them and come down to some idealized objects, which classically thinking just are defined by giving their position, which is a point in space, and their speed. So everything in the world is made up of those particles, composition or its composition of particles. Even if you don't believe in atomism, that everything in the end is made up of particle, ideally you can think of ideal extended objects as composed of divided these objects called particles, and those you describe by giving position and the velocity. So because they are so important, so they were put in as part of postulate that how to describe it. And our statement was, we had the postulate that there is an operator associated with position. So it was this X operator, and its spectrum was already defined. So these are the eigenstates. When we say talk about spectrum, we are giving the eigenstates and eigenvalues, where X can take any value from the reals. And similarly, there is an operator for momentum, which is given by this p hat, which was defined to be h k hat, where k hat had this spectrum, just like X. K belong to real. Sorry, by this I mean, it's just you have this operator k hat and p hat, which is the operator for momentum. Is just a scaling of that with a constant, the Planck's constant, just for historical reasons and for the matching of units. This k hat does not have the units, this spectrum, this does not have the units of momentum. While if I look at this operator p hat, it's clear that these states are also the eigenstates of this. This is the eigenvalue. So that means this k hat states is an eigenstate. A k state is an eigenstate of this momentum operator with eigenvalue h by k, and I can call it p. So these states, k states, I can label them as the p states as well with this identification that I'm putting in over here the corresponding eigenvalue. These are eigenvectors of the momentum operator as well, and whatever is the eigenvalue of this operator, I'm labeling the state by that eigenvalue. And there is just an identification between this label and the previous label through this relation. And this k actually has the units of inverse length. And this h bar, you need it to give here the units of momentum. And this has the units of what we call action. Now, and how is this different from x? This is also was part of our postulate that what is this k hat? Is that state whose components along the position eigenvectors are given by this. So that's completely defines these two operators and their eigenvectors. Now, what is the physics contained in it? How do you answer specific questions? So your one question could be, if particle is in state psi, some state, any general state, what is the probability of finding it at a specific position x and x plus between specific position x and a small interval around it? Because position is a continuous variable, so there's no meaning in saying what is the probability at one specific position. You have to pick up a small length around that position. So the probability of finding the particle between x and x plus dx, if it's in this state psi, if you measure its position, what would be the probability that you find it at any given position x? So it would be, as per the postulates, you take your state, take the scalar product with the eigenvectors of the corresponding operators, which are in this case are x. You take the mod square, and since it's a continuous variable, you multiply it with dx. This object gives you the probability density. Now, this guy, which are just the components of psi along the position eigenvector x, they are written like this as well and given a name, wave function. So this probability you can write as wave function mod square dx as well. So it's a wave function, it's a function of, it's a complex number. It's a complex function of one variable. So you can probably try to draw it. Maybe it's a complex variable, so you can draw it on paper. You can draw its real part, or you can draw its mod square. So if you draw it, this level at each point is telling you the probability density to find the particle at a specific point. And how would you get the probability then that particle is between a range? Then obviously it's just, this is your density. You integrate it between a and b. That's the probability to find it between A and B. But then what would be the total probability? Ability of finding the particle anywhere. According to this expression, it should be given by this. But if it's a properly normalized probability, then this probability should be equal to 1. The particle is somewhere along. You have only one dimension. So particle must be found somewhere. So the total probability of finding it in any range must be equal to 1. So this condition, this is essentially, this is normalization condition. It's actually the same normalization condition which we had put on the state vectors, because this expression is nothing except this. If I write it in the other form, this is equal to, this is x psi mod square, but this is equal to psi x psi. But that's an identity. This x and x integrated is equal to identity operator. So this implies, this is just saying psi by psi is equal to 1. So it's the same condition. And if psi is normalized, then your wave function would be normalized as well. Or the other way around. If you normalize the wave function, then this wave function is giving you the components of a normalized state vector. Now, so you are given that your particle is in the state psi, what would be the probability of finding the momentum? Again, momentum is, in this case, have a continuous spectrum. So again, you have to talk about probabilities, densities, and probability would be finding the momentum between a value p and p plus dp, around that value. So what would that be? Well, you can start by call p is equal to h by k. So we can identify, as we discussed above, we can identify these states, momentum eigenstates, with eigenstates of the k operator. Via this thing. So this is equal to h bar k hat k, h bar k, k. So this is the eigenvalue of k. So therefore, k is identified with a momentum eigenstate if you give the momentum label p to h bar k. Therefore, if I talk about probability being between p plus dp, that would just be equal to the probability of getting the k value between k plus dk, where k is not any k, it's this one. You have a specific number for momentum in mind, you get the k by dividing by h bar, because that's the identification. And dk is similarly dp over h bar. So this probability we know by our postulate is just this. And these components, we had given them a name, psi tilde. And dk, I can write it as dp over h bar, where the psi tilde, these are again complex function of one variable, and the variable here is k. Is this by definition, because that's how I gave it this symbol. And I can include, this is just a review of what we did in like the first few lectures. I can include an identity. So this thing is 1 over under root 2 pi e to the minus ikx. And this is just the wave function. So psi tilde of k is the Fourier transform. Now, if I put in this identification, then psi tilde of k e to the minus iota p over h bar x psi x dx. Now I want to describe it with the other label. I want to call it something like this. Psi tilde of p. So how can I, what would be the best way to do it? So if I go back, that the probability of finding the momentum between p and p plus dp is going to be this. That's what we have written here. So I can include this part over here. This is just a real number, and make the mod square of this quantity and write it like this. Then I can redefine psi tilde of p. Then this probability of p finding momentum between p and p plus dp will look like this. So then psi tilde of p mod square dp is just the probability around p. So then by our very definition, it must be this. So I can say psi tilde of p is p psi, where psi tilde of p is simply this redefinition, and which gives me this formula. So it's the Fourier transform, but with this scaling. And this all has come up because foolishly we have defined this. We insist on not using k hat, rather we want to use p hat, which is a scale version of k hat. So that constant is just scaling our formulas at different places. So this also implies that this thing would be, well, from here I can write p psi and including an identity dx. This is psi of x. And now I compare with this. That means this object is just this. The complex conjugate of it, because I have flipped this sign. Well, this is exactly this. So that means p x, the components of the momentum eigenvectors in the x basis are these. And it is normalized because k was normalized. We have derived all these formulas using the normalized eigenstates of k. So you can say that this normalized eigenstates of momentum in position basis eigenstates in position basis look like this. So if you think of it, if I look, for example, at its real part, it's a sinusoidal wave with a fixed wavelength. Wavelength is defined in terms of this wave number. Because from here, the wave number of this wave is just p over h bar, which is k. So many a times, well, I'm very used to of putting h bar is equal to 1 and just work with the wave number. And this operator is also called the wave number operator. You can work with wave numbers, and in the end, if you want your answer for momentum, you can convert from, you can go from k to p to this relation. I'll probably do that at a later point. I'll stop putting in h bar, but for now, I will keep the h bar in there. So any question so far? Can you hear me?
No, sir. Yeah, we hear.
Okay, now suppose we know what is the momentum of the particle. Okay, suppose we are sure about the momentum of the particle. And we know that is p. What would it mean? It means that probability of having momentum anything except P is 0. Or you can simply say that this means that the state of the system is this eigenstate. Remember, any state you can expand in terms of the eigenvectors of any Hermitian operator. And once you expand, these coefficients give you the probability of getting this answer I. But if you say that you are sure that it's in state in with momentum P, one specific momentum, that means all the other coefficients are 0 and psi is just P. If you know the value of a Hermitian operator, what is the value of it in a particular state? If it's a specific value, then it would be one particular eigenvalue. That's what it means when you say it has a specific value. It's one of the eigenvalues because only the eigenvalues can come up in your experiments. And if you are sure you know this about the state, that one particular eigenvalue will only come up, it has a 100% probability, then the state is an eigenstate of that operator with the specified eigenvalue. So in this case, I'm saying that the eigenvalue of a momentum, I'm sure, is going to be P. So psi is just P. And since the eigenvalue spectrum is non-degenerate, these guys for all P form a complete basis. This is all part of somehow the postulates. So there's no other index. This is just one particular state because a direct sum on these gives me not a direct sum, I mean a linear combination of these things. I can write any state as a linear combination of these, where these are just these guys. So I know that the state is now this. So psi is P, which in position basis looks like h bar x. So what is the, now you ask the question, what is the position of this particle? Well, you immediately say that you cannot, every time you ask what is a certain quantity, your postulate tell you that the answer is going to be one of the eigenvalues, and to each eigenvalue you can define you can assign a probability. So the answer is, what is the position of this particle? You say that I'm going to give you the probabilities. So the probability of finding it around a particular position x is just which is just and px is just but this is just equal to so it does not depend on position. That x does not appear anywhere. It just dropped when you took the mod square. So all positions are equally likely. No matter what x you choose, you get the same answer, same probability. So all positions are equally likely. So this is kind of a peculiar situation. You were completely sure in a state, I should say, let's not use very colloquial language, in a state where you are completely sure of momentum outcome. There's no uncertainty in momentum. Why? Because you know that this is the only value which is going to come up, P. So you're not unsure about anything. You're not sure that it's going to be P1 or P2 or P3. It's just going to be this specific value, P. So in a state where you are completely sure of a momentum outcome, you are completely unsure about the position outcome. One should write completely uncertain. Completely uncertain means not only like in general you are uncertain in the sense like it may show up here or it may show up there, but you have some level of knowledge, a probabilistic knowledge, that this place has more probability than that. Here, your knowledge is telling you, you still have a knowledge, the best knowledge which your state allows you to have, but that knowledge is telling you that each position is equally likely. So you are completely uncertain that where it will show up. By the way, from here you can also see that this kind of state, if I add these probabilities, it's going to blow up. Because these momentum eigenstates, just like these position eigenstates, they're only normalized in the sense of delta function. They're not themselves normalized. They don't give you this kind of, these things kind of blow up. Now, now suppose we know the position exactly. What if we know the position exactly? That means your state is then this position eigenstate. Because in a position eigenstate, you are completely certain about getting this eigenvalue will turn up if you measure the position. Now you ask, what is the probability of getting a momentum between P and P plus dP? So it's going to be proportional to this. But again, this is just equal to e to the minus I px over h bar does not depend on P. So all momenta are equally likely, equally probable to have any momentum. So this is a reciprocal relation. If you know about the position exactly, if you're sure about the position, you don't know anything about the momentum. And if you're sure about the momentum, then you don't know anything about the position. We can see the shape of these particular states. See the shape of momentum and position eigenstates. So if you have your state as some particular position, then you're sure is going to be in some position, I can find its position eigenstate wave functions. Let's say eigenstate wave functions. You cannot draw the states, that doesn't mean anything. But if you pick up their components along some basis, and for example, along the position basis, then that position basis has a continuous label, x, and the components are complex numbers. So I can, for example, draw the real part. So this guy, if I look at its components along the x basis, we know what it is. It's just the delta function. So here is somewhere x dash. So this state, position eigenstates, state looks like a spike at this position. And since this is a psi of x, and we know that psi of x mod square, it tells us about the probability of finding the particle at position, at any given position x. So what this picture is telling me, that at all these places I have no probability of finding the particle. It's all concentrated at x dash, where you have a spike. While if I consider the shape of momentum eigenstate, its wave function, let's write it as p, this looks like so if I draw this, its real part, it's a complex one, so I can draw, for example, the real part. It looks sinusoidal, but it's a complex wave, and when I make the mod square, they all give me one line, constant line over there. So so this wave is present everywhere, and it keeps going. It's just a pure sinusoidal wave which doesn't drop off. So that's why the probability everywhere is equal. So momentum eigenstates, they look like pure waves with a specific wave number or specific wavelength. Which is given by, this wave number is given by this k. And wavelength is just 1 over k. So this pure wave and wave number, so momentum eigenstates are pure waves, and wave number tells you the momentum. If your k is larger, if your momentum is larger, it will be a more tightly packed wave. And if your momentum is smaller, it will be a broader wave, because wave number would be smaller. This wave is not a pure sinusoidal wave, but since we know that these guys form a basis. So this wave can be written as a linear combination of the pure sinusoidal waves. And we know how to do it because this is just the delta function, which we know is something like this. E to the iota p x minus x dash dp. So the correct way to think about this formula, that's just an identity, but we can now think about it like this, that you have these pure waves. This is a pure wave, and here is your, well, there was a h bar. This is your wave number, k, and you're adding them up. And you're adding them up all with equal amplitude. So this guy has this wave in it, and this wave, and this one. So all possible sinusoidal waves are present, and they are present with equal probability because there's nothing multiplying them here. This AK is 1 for all of them. So all these waves are present. That's why any one of the momentum can turn up. Momentum is related to the wave number of these waves. And all these waves have equal amplitude. So all of them are equally probable. So that's why in the position eigenstate, you are completely unsure about the momentum. So this formula, when we write for, let's write it in general. For any eigen basis, we call it in mathematics linear combination. In quantum mechanics language, this is also called, this is the same thing which we call superposition. And over here, all you are saying is that you have, if you pick momentums, your any state would be a superposition, can be written as a superposition of momentum eigenstates. And since it's a continuous label, it would just be, these coefficients will be given by this. This integral just represents the sum, and this is just coming in here. And this guy is giving you the amplitude of each of the wave. So in this superposition, these guys are the amplitudes. That's just the terminology. So these Fourier transforms, which were Fourier transform, but let's just call them amplitudes over here. These are the amplitudes. So that's what was happening over here. You have all these waves. You can shift it, doesn't matter. And these waves all have the same amplitude. And the amplitude in a superposition, what it does, tells you, it tells you the probability of getting any particular one of them turning up in an experiment. So in quantum mechanics, when you make a superposition, then the resultant wave, it's not like that if you have a superposition of, let's say, 3 momenta, that if you measure, you will get some kind of a sum of those 3 momentum or average of those 3 momentum. You will only get one answer, one of those 3 momenta. And which one turns up is pure chance, but with a certain probability. So for example, my state could be now if I ask, it's a superposition of 3 waves. And this A1 is just telling me the size of this amplitude. A1, A2, and A3 of these 3 different waves. One of them is a K1 wave, this is K2, and this is K3. But when I measure, I don't get some kind of an average of these waves. My wave function becomes a superposition. You just draw, you just add these things to draw your resultant wave function. But the probability, but when you measure, you don't get some kind of an average. You get either this or that with the probability given by the relative amplitudes of these waves. So any question? Now let's take
सर ये जो साई है ये कंप्लीट एक वेव नहीं होगी,
ये एक
यानी वो
वेव
तो
है,
ठीक है क्या?
ये एक वेव है।
ये एक जी, तो और जब हम इसे ये मेजर कर रहे हैं तो ये कोई सी भी एक का ये देगी?
नहीं, मैं यही बता रहा हूँ ना कि ये एक वेव है, आप इन तीनों को ऐड करें, सुपरपोजिशन बनाए, आपके पास कुछ ऐसा कुछ वेव आएगी।
ठीक है,
बीट्स होंगे आपके पास क्योंकि 3 से वेव्स हैं, ये वेव आएगी, ये आपका वेव फंक्शन है, एंड इट्स अ रिप्रेजेंटेशन ऑफ दिस साई इन एक्स बेसिस। मगर मैं ये कह रहा हूँ कि ये जो वेव फंक्शन है, यू विल बी एबल टू रिजॉल्व इट इनटू प्योर वेव्स। प्योर वेव से मेरा मतलब है साइनोसाइडल वेव्स।
ओके,
तो आपके पास ये कंप्लीट वेव है और आप ये सोच रहे हैं कि सिंस इट्स सुपरपोजिशन ऑफ दी साइनोसाइडल वेव्स, तो जब मैंने मेजर मोमेंटम, आई गेट सम काइंड ऑफ अ मिक्सचर। यू डोंट गेट अ मिक्सचर। इस रेजोल्यूशन का जो मकसद है वो ये है आपको प्रोबेबिलिटीज देना। सो इफ यू आर गिवन दिस वेव एंड यू वांट टू फाइंड द मोमेंटा, पोजीशन तो बहुत सिंपल है। अगर आपको वेव फंक्शन दिया है, इफ दिस इज द शेप ऑफ द वेव फंक्शन, तो पोजीशन ये है कि आप इसको बस मॉड स्क्वायर करें, जहां पे वेव ज्यादा है वहां पे आपको पोजीशन की प्रोबेबिलिटी मिल जाएगी। अगर आपको मोमेंटम फाइंड करनी है तो इसको रिजॉल्व करें इन प्योर साइनोसाइडल वेव्स, which is essentially the problem of Fourier transform. So resolve it in pure sinusoidal waves, and their wavelength correspond to a particular momenta through this. और इसको रिजॉल्व करें, देन जिस वेव का एम्पलीट्यूड ज्यादा होगा उसकी प्रोबेबिलिटी ज्यादा, बिकॉज दैट्स व्हाट एग्जैक्टली आवर postulate says.
थैंक यू।
इसको भी हम in practice कुछ करेंगे तो then it will be more clear, but let me first do let's take a very particular state. So the state, I can define the state. Usually that's how it will be done, by defining its component in a particular basis. So let's give it, the state is defined to giving its components in the x basis, and we know that we call these things as wave functions, and the wave function is a Gaussian. And right now I'm taking a real wave function. in the end, I'll make a comment that you can slightly change it, make it complex, and not much will change. So you have a Gaussian, and this it will have some width. A Gaussian is completely defined by its height and its width. So width is controlled by this uh, this parameter A. Now this guy, if I want to work with normalized state, then we had seen that that's the same statement as that the wave function itself is normalized. That's the whole point of normalization, that the probabilities should sum up to 1. So the position probabilities sum up to 1, and that's the condition for normalization of this wave function. So to make it normalized, I can add some constant over here and then fix this constant so that the probabilities add to 1. So if I take it like this, then this gives me a mod square e to the minus 2a x square dx is equal to 1, and the Gaussian gives me this integral. So that gives me a mod square as 2a over pi half. So a is 2a over pi 1 by 4, and I can include some phase because I only found a mod square. A could be given a phase, but I don't really need it because it's an overall phase. If I'm describing a state, an overall phase, unless I am adding this state to some other state, then we know that the relative phases matter. But if I am just, this is my complete state of the system, then in the complete state, we have discussed the overall phases don't matter. So we may as well take this phase to be 1 and just choose this a to be 2a over pi 1 by 4. So since this Gaussian has width and it's a real one, so if I draw, I can on this same graph draw psi mod square. So this would be the shape of psi mod square. And so I will have, if I ask where is the particle, then the particle can be anywhere. It has actually not decided its mind. The correct question is that if I measure, what would be where will the particle turn up? So it can turn up anywhere over here, and these heights are telling me the probabilities. So this kind of situation, you say that you have an uncertainty. Uncertainty in position. Uncertainty is just a fancy name of saying that we don't know where it will turn up. There's a range over here where it can turn up. Well, in principle, it can be found anywhere because the Gaussian is never 0, so the probability is strictly not 0. But practically speaking, all the probabilities is concentrated within 2 to 3 sigma, 2 to 3 standard deviations. So just like the usual measure of the width of your probability, you can quantify this uncertainty, and we had discussed it through, we had said that the uncertainty we will call uncertainty in and observable O would be just, so these are the possible values of O, and this is the average square probability of these possible values of O. Just the usual formula for the variance. So uncertainty is just the variance. Well, I can, if I want, I can take a square root. So let's call it standard deviation. So I can, just by looking at it, from my eye, I can tell that it's going to be concentrated over here. So the width of this Gaussian is quantifying for me what is the level of my uncertainty. It's going to be most probably be found somewhere here. So this width is my uncertainty in position, and exactly I define it like this. So this uncertainty is denoted by delta x, and delta x square, the variance, according to this formula, x average probability dx. What is the average of x? Average of x, this was our formula, that in any state psi, we can compute the average through this. And why it worked? Because it was just this, putting in two identities. This is psi star x, this is psi x, and this is an eigenvector. So it picks up x dash, and this gives me, and I'm left with xx dash. And this gives me delta. So I can do the dx dash. So I get psi mod square. And this makes perfect sense. This same thing, in principle, this average should be your possible values multiplied with their probabilities and summed. And that's exactly what this formula says. Possible values, x, multiplied with their probabilities and summed. So in this case, it's quite clear that the average is 0 because I hadn't this is I mod square. I should use the normalized one, but normalization factor doesn't enter. It's an odd function, so it's 0. If I want it, so that means this, it was because this Gaussian was placed at x is equal to 0 and is symmetric, so equal probabilities on both sides, so the average is 0. If I had used something like that, then I would be putting my Gaussian at b, then the average would turn out to be b. So in any case, the average is 0. So that means when I am computing the uncertainty, so in that formula, I had x minus average, square. So this average is 0. So I can just take x square. probability of having x dx. So the probability is psi mod square, which gives me a mod square. To ax dx. And did we find a mod square? So a mod square was 2a pi 1 by 4. What was it? 2a over pi. It is being squared, so you have a half, and we need this integral. I always forget it. Let me quickly derive it. So we have over a. So if I do d by dA, I get under root pi as it is. Here I get minus half a to the minus 3 by 2. And when I apply this derivative in here, I bring down a minus x square minus half so that means square e minus ax square. The first moment is pi over there. So that means this uncertainty, here I did it for a, here I have a 2a. So this integral gives me 1 over 4a pi over 2a. So this 2a cancels with this 2a. And this pi cancels with this pi. And the uncertainty square is 1 over 4a. So delta x is 1 over 2 under root a. So then it's kind of clear that this is controlling the uncertainty. If it's large, uncertainty is small because uncertainty is 1 over under root is 1 over 2 under root a. So if it's large, uncertainty is small. If it's small, uncertainty is big. Now let me ask, what is the uncertainty of this thing? What is the uncertainty in momentum? So in other words, I want to ask the same question, probabilistic questions about the momentum. So first of all, what is the so let's ask this one. What is this? So to get this, I will have to have probabilities for momenta and then summed. So I need this and I need this. So I know how to compute the probabilities of momenta. They are given through, from what we have done, through this Fourier transform. So we need this guy, which is just this. And this gives me a kx e to the minus ax square dx. And this I can find, this integral, by completing a square. So I get e to the minus so to complete square, I can add this and subtract this. Now, so when I collect this, I get e to the minus a x plus k over 2a square. And I have, from here, I get, this is left. So minus minus plus, iota square gives me minus. 1a cancels with that a, and I get k square over 4a dx. So this comes out, it has no x. So if I shift the argument of the Gaussian by a fixed number, even if it's complex, the value doesn't change. And I get from here under root pi over a. Now, if I put in the value of a, the capital A, I have this. No, so pi is cancel. I have 1 over under root 2a and 2a, let's leave it like this. So this is what I get for these amplitudes a of k. So these a of k are giving me the probabilities for momenta, because from k I can construct p. So wherever there is k, I can just scale it to get p. And I get that this k is also turned out to be real. But what is more important, that if I square it, इसको मैं square वैसे लिख देता हूँ. This is just a number. Doesn't depend on k. So distribution is again normal distribution. Or again, you get a Gaussian. So the momenta are also have an uncertainty. You won't get one particular momentum. You're not sure which one you will get. Well, you will get one particular, but you don't know which one you will get. There's a probability that you will get this one, this one, this one, this one, this one, this one, or any one of these. And the width of this Gaussian is controlling for you that what possible values of momenta are possible. Now, it so happened because of the way we had chosen our wave function, starting wave function, that it's peaked at k is equal to 0. So the most probable value is that you have 0 momentum, the particle is still. But the other positive and negative momenta are also possible. So the particle, you could find the particle is moving to the right or to the left with various speeds depending on this width. So let's compute this width. Now the probability so since this wave function gives me the probability, this one, this is the just exactly the probability of having k between k plus dk, or having momentum p or p plus dp, where p is equal to h bar k. So I can use it to compute this. And since average of momenta turned out to be 0, so it would just be p square and the probability. So this turns out to be p square, and then I put the mod square of this. So the mod square gives me just the mod square of this, 1 over 2a, 2a over pi 1 by 2, and I have, so the probability of having momentum was, probability p having momentum p was psi mod square dk. This I can write as psi k replaced with p over h bar, and instead of dk I write dp over h bar. So just what we did in the beginning. So I have an h bar over here, a dp here, and then I can just write psi of k, which I have found, and replace k with p over h bar. So I had k square over 2a, so that becomes e minus p square over 2a h bar square. So is this clear? This is a of k. A of k mod square gives me the probability of being between k and k plus dk, and that's same as the probability of having momentum around p. But that's the probability. So this dk translates into dp over h bar, so that gives me an extra h bar here. And in psi, I can just replace k by p over h bar now. It's just the change of variable in this integral. So now I can just do this integral, which we have already done. I get, what was my answer? So it's the first moment of the Gaussian. So I get 1 over 2 times A. So A in this case gives me this, because I have to invert that, times under root pi and under root 2a h bar square. So this under root pi goes, this 2a goes, this h square goes away with this h bar, and I'm left with an h bar square, and then I have a 2a times 2a under root, so that gives me 2a h bar square. So that gives me dp is equal to under root 2 under root a h bar.
फिर डिनोमिनेटर में भी तो एक और 2 है, तो वो नहीं जाएगा?
कहाँ दिखाएं?
नीचे देखें, डिनोमिनेटर में भी तो 2 था ना एक,
हाँ,
तो वो चला जाएगा ना?
ये खत्म
Divide.
हो गया? ये किससे
हाँ,
डिवाइड होगा?
ये अंडर रूट 2 2 बचे हैं इन द न्यूमरेटर, और डिनोमिनेटर में
अच्छा,
2 था,
अंडर
तो
रूट कोई नहीं, इसका अंडर रूट कोई नहीं बचा. I have
2 ही
only
नहीं
this.
बचा.
हाँ, कोई 2 नहीं बचा. So that's all I have, right? Is this fine, right? अब ठीक है ना?
Yes sir.
हाँ.
जी सर.
So now if I do this product, this is just a curious observation. Then what was dx? It was 1 over 2 under root a. And this is under root a h bar. So that a, the width got cancelled. And the product of uncertainties is equal to h bar over 2. But more important from width getting cancelled is the fact that dx is 1 over 2 under root a. So if I make something like a Gaussian state and I want to fix the position more precisely, then I will have to make a large. But that will make my uncertainty in momentum go up. On the other hand, if I want to have momentum to be known more precisely, then I will try to make a small. But that will increase the uncertainty in position. So position and momentum uncertainties are reciprocally related. And for Gaussian states, no matter what the width is, you get this exact equality, which says when one goes up, the other goes down. And you have a constant of proportionality in terms of h bar over 2. So this is called Heisenberg's uncertainty relation. This relation, I derived it for the Gaussian states. You can make a more general statement about these uncertainty relations between uncertainty in position and momenta in any state. And actually, you can make similar statements about other observables, other observations. And those are the generalized uncertainty relations. I'm going to just discuss that in a moment. So just give me 3 minutes. I'll be back in 3 minutes. So I'll be back in 3 minutes. So suppose you have two observables, A and B, and their corresponding Hermitian operators. Or Hermitian. Then I can just compute their commutator. And whatever the commutator comes out to be, it will be an operator. And I write that operator like this. So if I write it this way, the nice thing about then the C operator is that C is Hermitian. Hermitian 2, you can easily check. C is AB minus BA times minus iota. So C dagger is iota. When you take the dagger, the order reverses. But B dagger is just B because B and A are Hermitian. So you can again reverse the order by taking a minus out. They're all operators, so I put hats on them. And this is a C. So C is Hermitian. Now consider any normalized state psi. And so this is completely general state, and I just compute the uncertainty product in this state. So that would be just this. Because you can insert, we had done this, we had derived this, that you can write the uncertainty as operator relation, because you can insert the complete sets in between and it will just pick up the eigenvalues. So it would be just the just like I did above, it would just be, this would just be equal to this formula. That's same as this. We had derived it before, so I just don't want to do it, and you just have to put in two identities here and you'll get this, exactly this relation. So you get this product. This is the first and this is the second. Now what I do, just to make things more readable, let me call this a new operator A tilde. Which is shifted with this average value, and B tilde like this. Then you can note, even with this shift, when I compute the commutator, that still comes out to be the same. because a shift by a constant doesn't change the commutator. You can quickly check. This is just so the commutators. We haven't done these many identities, but the commutators just break. Minus minus but these are proportional to, this is just a number, so this is actually this. Since they are proportional to identity, so they commute with everything. So these are 0 and it's just equal to iota c hat. So with this shift, the commutator doesn't change, and I can write this product of uncertainties as now. There's another thing you can notice. Since this part is Hermitian, so this whole thing stays Hermitian. This was Hermitian. Sum of two Hermitian operators is still Hermitian. So I can write it as, that means this Hermitian, since it's Hermitian, I can break this up and this can act back because it's Hermitian. So I can write them as these guys, where A psi is just this vector, which you get by action of A on psi. So now you can use Schwartz inequality, which essentially says that if you have two vectors and you take the norm square, then this product is bigger than the scalar product normed square. So I have this norm square of first vector, and this is the second vector. So that means I can write is greater than, so here comes the first vector, A tilde psi, B tilde psi, mod square. Now, this is just this psi acting on A and B acting on psi mod square. But since they are Hermitian, so they act both ways. So I can just write it as just normal A acting and B acting on psi mod square. So that means I have this relation. Now over here, you have a product. I don't want to leave it as a product. So this is, you can say that this is a general relation of product of uncertainties, but I want to give it a better shape. First of all, I don't want to write it in terms of A tilde, but rather write it in terms of A. But more importantly, I want to write it in terms of a commutator, because I want to give it a shape more closely related to the uncertainty relation, which I suspect exists for X and P. And I know how the product of X and P behaves through this commutator. So I want to write the product as a commutator. So whenever you have a product, you can obviously break it into a commutator and an anti-commutator. So A tilde, B tilde is just A tilde, B tilde, A tilde over 2 plus A tilde, B tilde minus B tilde, A tilde over 2. So I have done nothing except added and subtracted B times A, the reverse ordered product, divided by 2. But this gives me then 1 over 2. When you reverse the order and add a plus, give it a name, it's called anti-commutator. And this is just the usual commutator. So I can write I have psi, and this operator gets replaced with this one. Sandwich between psi, and the whole thing mod squared. So this I can actually write, this is not greater than this is just greater than this. I can break it up, not the mod square, but this scalar product. One by 4 I can bring out. Now this guy, if I look at this guy, B tilde anti-commutator, this is just this. And if I take the Hermitian conjugate of this whole thing, it doesn't change. So that means this is Hermitian. And we know that if you have an Hermitian operator, then if I sandwich it between any state, I'll get a real number. Right? Because we can quickly do it. I can put in its own eigenbasis. This is equal to this. So this gives me, this is, this and this combined can be written as mod square, because this is the star of that. And this gives me the eigenvalues, let's say hi, which it picks up from here. And this was picked up to be the orthonormal eigenbasis. So I dash can be summed. This is delta I dash. So I can sum over I dash, I get this. These are the eigenvalues of a Hermitian operator. So these are real numbers, and these are positive numbers. So the sum is a real number, which I'm calling A. While this guy, the anti-commutator, it was anti-Hermitian, because C is Hermitian, iota C is anti-Hermitian. Or you can say that if I sandwich it between any two, I just comes out. And C is Hermitian. So C gives me a real number. So that means this sandwich between any state will give me a pure imaginary. Number, which I have written as iota times a real number. B is real. So that means this guy takes this form, A plus iota B mod square. So I know what is A plus iota B mod square. Sorry, delta A. So that's equal to A square plus B square. So this I can write as psi square, not mod square, just the square. Well, it doesn't matter because it's a real number. Now this term, this is positive definite. Therefore, we can write where C is just minus iota times the commutator. So another term, in other words, you can write this relation greater than or equal to I can bring out the minus iota outside. It will be minus 1/4. So if C is a constant A, let's say if C is equal to h bar times identity. So in that case, this is the form of our commutator. Two operators which have a commutator like this, they are called canonically conjugate. Conjugate pair of operators. And one of our quintessential example is position and momentum. So then it's telling me, if I look at this, one by four h bar comes out, this is just one. So delta A, delta B is greater than or equal to h bar, this was square, h bar over 2. So for position and momentum, this is the uncertainty relation. But this is the more general one. More generally, one over 2 psi c psi. Where psi c is defined through this. So you have a inequality. We got an equality because that was a very special state, but that was the minimum. So this is called, so because it's an inequality, so what you have over here is the minimum possible value of product of uncertainties. You cannot do, no matter what you do, you cannot do better than this. And anything else you will do will be worse than that. So the Gaussian, it turns out, is what we call a Gaussian is a minimum uncertainty state, or minimum uncertainty wave packet. And for the equality to hold, you must have, for equality to hold, you must have that this positive number which we had discarded, that should be 0, because we are then not discarding any positive number. But also the inequality was coming in because of Schwartz. So Schwartz gives us an equality if the two vectors are proportional. If you have a state in which a times psi is equal to B, A acting on psi is proportional to B acting on psi, then you have then you can have a minimum uncertainty state. So you can check that if I look in position basis, then the Gaussian in the position basis, the action of position is just multiplication by x. And the action of momentum, so A is like position and B is like momentum. Action of momentum is this. So it does become proportional to that. And this is same as this with a constant. So that does give you minimum inequality. And this part you can also check that it holds for it. So maybe we should stop here. I will post a lecture tomorrow. I will actually record it live. So if you want to join, you are welcome. Otherwise, I'll just post it up. So I'll do it tomorrow at 3 p.m. Any question?
Okay, sir. Sir, yes, sir. जब हमने Gaussian के लिए किया, then we it was equal to, and then जब हमने generalize किया तो it was less than equals to or
Yeah.
greater than equals to. तो it is Gaussian is a normal distribution. तो it's a particular case. तो उसके अंदर जो है वो exactly हमें पता है that equals to आएगा और generally इसके दिए जो है वो inequality
No,
आएगी.
that was just
That's the
I said कि वो Gaussian जो था, it was our luck कि उसमें equality आ गई. But it was our luck. Well, not really luck. It was because of these two conditions. These both conditions hold for the Gaussian. So if these conditions hold, then you will have an equality. So Gaussian is the best you can do if you want to minimize both uncertainties. Anything else will be worse. But even in the best case scenario, if you decrease the uncertainty in one, it increases in the other. Any other question? Okay, I'm gonna stop here.